So today we are going to start a new code sections in which we will see some important questions to understand the basic concepts as well as advanced concept. Okay, so the question today we have is 261. I'm going to start, right? So let's see the today questions, right? So today we are going to start with a new series in which we will see graph valid tree question of lead code 261, and we'll see that uh, the approaches, what are the approaches we can find out. Okay, so as you can see here, it is saying that the question, let's read the question first. So here you can see that question saying you have a graph of n nodes level from 0 to n minus 1. So you are given 0 to n minus 1. So you are given an integer n and a list of edges, right, where edges of I is a I and bi indicate that there is an undirected edge between nodes ai and bi in the graph. So what we have to do, we have to return true if the edges are given graph make up a valid tree. If this is a valid tree, then we will return true, otherwise we will return false. Okay, so this is the example first, and we are going to see, is this a valid tree graph, valid graph tree or not. Okay, so you can see node is 0 1 2 and 3 4. So input is given is 5, right? That's why total node is 5 from 0 to 4, and that's why edges are what, 0 to 1, this one, 0 2, 0 3 and 1 4. These edges are given. So now we have to check is this graph is a valid tree or not. Okay, so I think you have answered the question, right? So what we will assume that I will assume that you have a basic concepts of graph theory, right? And then we will perform a simple DFS, right? Depth first search, in which we'll see the you can find out the questions related to the DFS, and most of the textbooks on algorithm or discrete math have a section on it. Okay, so you can go and revise it. Okay, so now approach one is graph theory and iterative depth first search, right? So let's assume that what we have, this is the graph, right? Let's see, graph is G, right? We have graph G and is a valid tree, right? So this is a valid tree. How we'll say that? So till now we'll say that this is not valid or not, so we can take in hold, right? We'll taking it hold. So if G is a graph, so is a tree or not, if and only it can be happen, right? Means the condition is two conditions are there, if that condition will satisfy the graph, then the graph can be a tree, or only if these two conditions met, right? So if what G is fully connected, right? If G is fully connected, right? So as you can see, all the nodes are connected, right? 0 is connected with 1, 0 is connected with 2, 0 is connected with 3, and 4 is connected with 1. Like that, all the nodes are connected. It means condition 1 is satisfied, correct? And all the and there is a path between them also, correct? If someone is want to go from 0 to 4, he can go with 0 1 and then 1 to 4, correct? So that's here. Now condition 2 is what? Condition 2 is if graph G contains no cycle, right? So if it contains no cycle means what? There is should not be cycle, right? So as you can see, there is no cycle, right? If like 4 is connected with any on this one, right? Like this, like if this is connected, it means this is not valid one. But what is happening, there is no such edges, right? So that's why it is valid, it is true. Okay, so our given graph, right, we have what, how many nodes we have 5 nodes, that's given 5, right? And nodes are 0 1 2 3 4, and edges is given 0 1 0 2 0 3 0 1 1 4. So if we configure this graph, so it will look like this one, and so that this graph is what, fully connected and have no cycle, and so that we can say that this is a valid graph. Okay, so I think you understood now what is a if what is a tree we can make from a graph. So every tree is a graph, but that should satisfy some conditions, right? Similarly, if a graph is fully connected and have no cycle, it means that is a valid tree. Okay, now we will think about what another example, and in this example you can see that condition 1 is what saying. Condition 1 is saying if graph G is fully connected, if and only if we started a search in which we'll see that it connected with all. Yeah, is it fully connected? So you can say it is fully connected, but is there any cycle in the second condition? So you can see that we are going from here 0 to 1, that's okay. From 1 to 4 it's fine, 1 to 2 it's fine, all is well, here well, here well, here well, right? Now 2 to 3 that's also fine, but when we go back to here, right, so you can see that it makes a cycle, right? And that's why this is not a valid tree, right? And that's why condition is not satisfying. Okay, now I think you have understood, right, when a graph will be a valid tree, right? Now I will write some basic concept of DFS, right? Now you have understood already how to find out the tree, sorry, graph is a valid tree or not. Now if we'll talk about the DFS, right, DFS is depth first search, right? Depth first search. So depth search is a classic graphical traversal algorithm, right? It is a classical graph traversal algorithm. Some people also say it's a graph traversal algo, right? You can say graph traversal algo also, right? So DFS is we will use in which we have to traverse from one node to another, right? So this graph traversal algo graph can be can have two conditions, right? To check for both these conditions that we have discussed, right? Okay, this is fully connected or is it a is it a making cycle or not, right? So those two conditions. So if G is connected, right, what I told, if G is fully connected, how connected? Fully, right? And if and only if we started depth first search from a single source, let's assume the source can be from 0 and then we can move to next level, right? Right, like we have did. So if we'll start from here, it should go to what, this he can go to this one, then he can go to this one, right? Like that, right? Means if G is fully connected, if and only if we have started a depth first search from a single source, like I'll start from what, this node, root node, right? And I'll go to the child node, right? Subchild node, you can say. So we have to start from somewhere, that is we can call single source, and we have to discover all the nodes here, then we can go here, then we can go here. If there is some child, then we can move to here also, right? Now means we have traversed all the nodes, right, in G, right, when we are trying to search. Now we also have to find the second condition. G contains what? No cycle. If G contains no cycle, right, if and only if, then the DFS, depth first search, never go back to an already discovered node, right? If someone has already discovered, like let's say these are node 1, right, this node 2, and this node is 3, right? So if we are traversing from here, we have started from what, 1, and we are going to 2. Now again if we are going to 3 and after that we are going to back, right, means we have already traversed this one, means we have what, we have discovered node we already have, and we are going back to traverse again. Means we need to be careful through not to count trivial cycle, right? Like trivial cycle is 1 to 2, 2 to 3, or 3 to 1, like that. So that occur with most implementation of undirected edges. So if this is the direction, means we have the direction, means we know that, right? But if we don't have the given direction, means it is not given, right? In that cases, the most problem will come, right, during the undirected edges. So depth first search requires what? Depth first search requires being able to look up the adjustment, right? Adjacent, you can say, of a node, right? Like if we'll talk about this one, right, 1, and we have to look up for this one node. What are the neighbor nodes? So neighbor node is what? 2, or neighbor node is what? 3, right? So 2 neighbor nodes can be here, right? So first he will traverse what? These 2, and then he has to go to 3, like that. So likewise, many graph interview problem, actually they used to ask these questions, right? So we have to be very careful while implementing this one. We have to start from our node, right, and immediately we have to move to its neighbor, right? So what we have to think about, like we have to traverse one by one, and then we have to check is there cycle or not, right? So therefore our first step is to convert the input into adjacent list, right? We are talking about this one, all the neighbors, right? So what we should do, right, what we should do, our first step is to convert the input into adjacent list. Whatever the input is given, first we will make a adjacent list, we can say. So that adjacent list, like 1 having the adjacent list what? 2 and 3, correct? Similarly, if we'll talk about 2, adjacent is 1 and 3, right? And if we talk about 3, what is the list we have? 1 and 2, like that. We have to create a adjacent list like this, okay? So adjacent list is where we have a list of sublist, you can say, where each sublist is the list of the immediate neighbor. So if we'll talk about the previous one that we had here, right? So if we'll talk about 0, right, 0 has the adjacent list what? 1, 2, 3. Now if we'll talk about 1 has what? 4, right? And also 1, but 1 is already traversed, right? So that we have to also take care. Now if we'll talk about 2 has only one adjacent, 0, right? And 3 is also 0. So this is the adjacent list we have to prepare. Now how we will make the like if we'll talk about, we have given sublist, right? So how we will make the immediate neighbor of the ith node, okay? So first of all, we should always think about the little code, right? So if we have to create a list of list, right? So how we will write that? Always write list, then we have to make a list, right? Because we are making what? List of list, and this list is what? Integer, right? So and we have to give name like what? Adjacent list. This is our adjacent list, and this is what? New, you can say, you can take array list also, right? This is our array list. I'm writing the code like how we should start writing the code. Like some people used to afraid writing the code, how to begin, how to do that, right? So if you want to create a new list of list, right? New list of list means what? We have a list like this, right? So in list we used to take list 1, right? List 1, then we have list 2, then we have list 3, then we have list 4, like that we will go on, right? And what is this list? This list is internally, it's also contain some value, like what? 0, 1, 2, like that, okay? And this list is what? How? What is the meaning? It is similarly, it can be also 2, 3, like that. This can be like this. So internally it's stored like that. Wow, how we can say? If we talk about what we have in list 1, what we have? 0, 1, 2. this is our list, right? Again, this is, we can keep like that also. Okay, another is what, 2 3, this is a list and it contains at what, this, like this we can do. So this, if this is 0 index of the list, this is index 1 and it will be so on, 0 1 2 3 and so on. So this is the meaning of the list, right? This is the implementation level, right? So whenever, so if we have assume the internal we have 0, then we have 1 2 and 3, 1 is coming to what, 4. So these are node we have given, right? These are the node we have given. If we want to, represent this one as what, if we want to represent this was 0, right? So for 0, the first adjacent, if we want to make adjacent, right, the first list will come what, 0 will come, 0 have what data, adjacent 1, 0 has 1 2 and then 3, right? So this is the list, adjacent list we have for the 0. So it will come where, it will come to index here, or you can say this one, this position. Okay, similarly if we'll calculate for 1, right, it will be having the only one kid, right, neighbor you can say, and you can take this one also, right? So this list will come what, here. For if we'll talk about this one, this will come 4 comma 0, right? So this will be here. Okay, similarly we can calculate for this and so on, like we have maintained, right? I think you have understood this one, right? So what I'll do, I will clean it here, the below one. So I'm cleaning the below one. Give me 1 minute. Okay, now I think you have understood. Right, so we have understood that we have created what, we have taken array list, right? We have created array list. Now if we have to initialize an empty list for node, right? If we have empty list, right, for this one, this adjacent list, right, how we'll do that? We will make a loop, for loop, right? And this for loop will start from where? We will start from int I equal to 0, right? And this I is what, I should be less than n, means we have number of nodes given, right? So if we will start from 0 to n, like we have 0 1 2 4, like 1 2 3 4, so we will start from 0, we'll go to 4, right? And then I plus plus, you know, to make this loop. Now this adjacent list is empty, right? So now we have to initialize it, right? You can, how do we initialize this? So we have to make for all the kid, its children, all the index, we have to add some initialize, we have to initialize the value. This adjacent list is initialized from here, right? We have taken array list, right, like that. So this was initialized, but it's all the index is not initialized. So how we'll do that? We have to take the adjacent list and then we will dot add, we'll do add, and then we will pass a new array list, right? Like this we should do, right? So this will initialize. So first what we have created here, we have created a adjacent list that will contain our all the neighbors, right? Adjacent list, right? And then we have to initialize. How we have to initialize? Like this. So 2 steps we have to do, right? So now what we have to do, if we'll talk about the third step, right? So third step should what happen? So we have to go through the edge list and we have to populate the adjacent list. What we have to do? We have to go through the edges of the list and then we have to populate the adjacent list. How we will do that? We have to make a loop, right? We have to do for all the list, right? All the list item, right? So we'll take for loop and then we will take a int array, right? And then we will take edge, right? And this edge is what? Edges will come from what? Edges. So one was, this was already given, right? This edges is will be already given. So we will make the for loop and one by one edge we will take. And how we will do that? We will prepare the adjacent list dot, and then we will do what? Get. We will get what? Is at what? 0. Whatever the data we have at is 0, that is our first node, right? And then our source node, you can say. And then we will do add, and we'll pass the what? Is at is at 1, then its neighbor, right? So this is our neighbor we have given, right? Assume this one. Like this we will do. Similarly, we will take adjacent list right here, and then we will do get, right? You can write adjacent full adjacent list dot get, and then we'll take what? Is at what? 1. The next one, next it's a child, right? And then we will do what? Add what? Is at 0. We have to do like this. So now think, if you have understood, it's okay, but let's assume that what I am discussing. So sorry, here if you assume this one, right, we have given what? N is given, and then all the age is given. Similarly, if you talk about the first example, what we have age given, what? 5, and then we have given ages are given, right? So these ages are represented like that only. Okay, so what age is given? Age is given in the array form. It is saying it is 0 and 1, right? The first age is 0 and 1. How? 0 is 1, it is connected to 2, and then 3, and is connected to what? 4. Like that we have already given in the graph as well as given in the array form also. So next, if we'll talk about what is given, we'll take 0 1, and then we have given 0 2 0 3, right? 0 1 0 1 0 2 0 3, like that we have given, right? And next is what? 1 4, you can say, like that we have given, right? This is the array. So if we'll talk about the first one, this one, right? So we have assumed this one, okay, as well. So at a time internally, right, this is given. So what we will do, at a time 1 is, this is the whole list, right? This is the whole age list, right? The whole, it is representing this whole list, but only one item at index 0 is coming what? Here, correct? Is coming here. I think I should change the color. I was saying, so this is coming what? From this index 0 and 1, and but this array that we have made, this is what? Ages. We have ages, right? So now if we'll talk about the age, what age have? Age have 0 and 1, only 0 and 1 in age, not ages. So at index 0 is 0, at index 1 is 1, right? Means we are talking about this age. This is 0, this is 0, and this is 1, right? So we have to take adjacent list dot get at 0, means we are talking about this one. What we have? We will get, and then we will add again, means we will get, then we have, it means the list is given like this. So if we'll do adjacent list at get 0, means we have here 0, we have value what? Node is 0, right? So at this position, this index, we have a list, right? So at list 1, that we have list 1, so at that we have to do add, and then we will add age at 1. Got it? So we are doing like that, so that it will become 2D, right? We are doing here, this is doing on, you can say list 1, as list 1, adding on list 1. This will give you the list 1, okay? This will give you list 1. Similarly we are doing for this, and so on. It will add your all the neighbors, right? All the edges will come, and we will fill up our adjacent list. We will our adjacent list will be completed, you can say. Okay, now this part is done. So before you can say. So before we move on actual carrying out the depth first search, let's quickly reassure ourselves that an adjacent list was the best graph representation for this problem, right? So the two other choices would have been adjacency matrix and linked representation that we have seen here, right? What I'm saying, I'm saying like we have two things, right? What we have, the to represent this one, right? Graph representation, best graph representation. What we have, adjacency list, right? Adjacency list. I think we used right there. You check the spelling, okay? So adjacency list was the best way to represent our graph, correct? This is the best way to represent the graph. Okay, so we have what two choices we have to represent the graph, right? That is one way to adjacency matrix, right? I have talked about adjacency matrix, and another is what, linked representation. Like, so two way we can do that. So in the adjacency matrix, right, an adjacency matrix would be an acceptable, although not ideal. It means representation for this problem is often we would only use adjacent matrix if we know that the number of adjacency edges is higher than the number of nodes, right? So what we have to do, we have no reason to believe that in this case the approach 2 will be also provide some useful insight into this, right? That we will see, right, in the approach 2. So in this approach, right, what we will do, we will doing DFS, right? Similarly, if we'll talk about the link representation, right, what we will do, that a link representation where you make actual nodes object, right, and we would be an overly complicated representation, and that could suggest to an interviewer that you have a limited understanding of adjacent lists and adjacency matrix. So always, at least you should know this linked representation. There is only one purpose, to impress your interviewer, right? You should have the link representation little knowledge, right? So that you can show your interviewer that you are not limited understanding you have on the adjacent matrix, okay, adjacent list. So they are not commonly used in the interview question actually, but we should always know at least one more way, right? So anyway, so let's get started on the depth first search, right? And then we will recall the most depth first search follow template like one below. That we will use our iterative approach here. We'll see that approach, right? So what we have to see, that this doesn't solve the problem of determining whether input graph is tree or not, but we simply see the how we will write the code, okay? So let me write here below how we'll write that. First, if we use a stack to keep track of unexplored node, right, we will take that as we have taken, right? So we should take stack, and that this stack is will take integer, right? And this is our stack, you can say. Okay, now what we will do, we will initialize the stack, right? Sorry, not array list. This is our stack, right? What we have to, we will take we have taken this stack, and this stack will keep track of unexplored node, right? How we'll do that? First, initially we will take this stack, and then we'll do push, right? And what we will push, we'll push the first node, that is 0, and then we should use a set to keep track of already seen node to avoid the infinitely looping. And how we'll say that do that? We should always take a set or any other things you can take. I'm taking set, or you can take a list also, right? So I'm taking set that will keep our you can say not duplicate record, and that's why I'm taking scene, and it will avoid us to go into the infinite loop also. So this is the scene, and I'll take this as a has set, right? Because that is a interface, correct? So this scene is very, very important, right? Why? If we'll have this one, so we will not go into the infinite loop, right? Then we have already pushed this in node 0. Now what we will do? We will add scene. On scene we will add this 0, like we have already traversed, we have seen this one, so we will not go on here, right? Then while there are nodes remaining on the stack, what we will do that we will make a loop, right? And this can be our while loop. So first we will make question mark, right? And then we will say that stack dot is empty. A stack is empty. If stack is empty, if we have stack is empty, then we will go into this loop, right? And then we will say that int node will take a node, will take from what? We will take from this stack, and this stack will do the pop, right? So we have get the first node, right, from the stack, whatever the top node we have, and then we will take off to visit, right? How we'll do that? First we will check for unseen neighbors of this node, right? How we'll do that? We will make a loop, for loop, right? And this for loop will take first its neighbor, one by each neighbor, not neighbor. You can take neighbor, nei neighbor, and this neighbor will explore our adjacent list, right? How will do that? We have already created our adjacent list, right? From the adjacent list we will do get, right? And we will pass our node. So once we will pass our node, what will happen? Each neighbor will come here one by one, okay? And we'll see if this is in the our list. How will do that? We will make our if condition, first if condition, and we will check on scene. If scene dot contains, right? Because that is a set, and set have this neighbor, nei, you can say neighbor, then what will happen? We will continue, right? We will not do anything, means we have already, it means we can say that we have already here, already present, you can say, right? You can mark this line. Now we will push. If that is not on the stack, then we will push on the stack, right? We will take stack dot push, and then we will pass our neighbor, right? And then on the scene we will add on the scene, and the scene is what? Nei. And similarly we will close all the remaining here, okay? So you will try this one and you'll check if this is this approach will work for you, right? And fine, otherwise we'll go to the coding section and we'll.
The graph is fully connected, right? And there is no cycle, right? So if the graph is fully connected, means if the graph is fully connected, right? If the graph is fully connected, means what we have to do to understand means every node, either this, or this, every node must have been seen, right? And so that it means that all the node must be in the scene set, right? that we have we have taken, right, at the end, because a set removes duplicates and only values goes into it, right, where valid nodes number, right, then we know that the graph was fully connected or not, right. So this graph is fully connected or not, right. How will you see that? Only if and only if the scene set contains n value at the end. So here we have to make a simple note, right. We have to return true if and only if the DFS search discover all node, right. Means what we have to do, we have to sorry we have to return true, correct. We have to return true if and only if the DFS discover all nodes, right. If you'll say discover all nodes, correct. And so that what we have to write, we have to write return scene dot size, right. Now scene should have the size is equal to the given number of nodes, right, that is n. This should be written. So make sure when we are comparing, right, the size equal to n, right, if that is equal to n, it means we have to return true and the graph is fully connected. Okay, so for this is the first check, right. In the second check, what we have to what you have to see, you might be thinking, can't we modify the above algorithm, right, that we have discussed right now to return the false, right, when never is in a visited. Means if I'll write here a condition, right, sorry, if we write here if scene dot contains what, never, I'll take any, okay, and then we will make a condition what, return false, correct. So two conditions is there. The first, if it is fully connected, right, and another is what, if scene contains true any, then we will return false, right. Means when we have to return what, false, when never is in a visited. If never is already in visited, then we have to make this line of changes in our code, right. So these two cases will improve our algo, right, our program. So however, this will only work on the directed graph, right. So if we talk about these things, right, so if this is the direction, right, like this direction is given, right, then it will work, right, directed graph. But on an undirected graph like the one we are working on, right, let's take an example, right. I'll take here example. The trivial cycle will be detected. Let's assume undirected is a and it going to b and b is going to c. This is a trivial cycle, right, trivial cycle. So this trivial cycle will be detected when, if we'll take an example, so if there is an undirected edge between a and b, right, here this is a and b, a node and b node, right, a detector cycle will be include a to b, b to c, right. But if c is not there, we have a, right, means this is our trivial cycle, right. Means directly or indirectly what is happening, we have a node a, we have b, right. So there is a node, right, a to b, and now we are doing what, b to a, right. So this is our trivial cycle, got it. So this is because an undirected edge is actually two edges in the adjacent list, and so it's form a cycle, correct? So there is several strategy to detect whether or not an undirected graph contains cycle, with including the trivial cycle. Mostly we have to rely on the idea that the DFS, depth first search, right, should on go only go along each edge at least once. Okay, so therefore only one direction we have to choose at a time. This means that we will not get the cycle, right? And it means that when we go along an edge, we should do something to ensure that we don't then later go back along it in the opposite direction. If we have came A to B, right, so it is not required to go to A to B to A again. Either we'll follow this path or this path, right? Not at a time, both time. Okay, so here are couple of ways of achieving this, right? If I'll talk about the strategy one, let me go to here. Okay, if we have the strategy one, a strategy, we'll say a strategy one, right? So the first strategy is to simply delete the opposite direction edges from the adjacency list. Okay, all the opposite direction edges from the adjacent list we will delete, right? What we have to do? Remove or delete, you can say, remove or delete the opposite direction edges, okay, from adjacency list, correct? First we can first strategy we will do like this, right? And if we'll talk about the representation, it means what? A to B will take, and what we will do? B to A we will remove, this one we will removing, and we will taking only this. Got it? Previously it was what? A to B and B to A, right? So we are only taking this part, and we are not going to the reverse part. This is opposite one, right? This is opposite direction. So we will remove this one. Okay. So now if we'll talk about what? If we will talk about the algo, what will be our algo? Okay. So let me go here, right? What we will do there? First we will check while there are nodes remaining on the stack, right? We will make while loop. You know that in the while loop, first we will check on our stack. If stack is what? Empty. So that we have the function is empty is a function, and we will check is this empty. If yes, right, means we will go into the loop, in which the first we will from the stack will do pop. We'll get the top element from here, the stack, and that is our what? Our node, right? That is our node. So we have to take off to visit, right? The first element will get from the stack. Now, as we have discussed previously, similarly, what we will do? We'll make a loop and we'll get all the neighbors one by one, each neighbors. So I'm taking neighbor as NEI. You can take full name also, neighbor, like this, neighbor, and then this neighbor will come from what? Adjacency list, right? Adjacency list, and we'll get one by one all its neighbor nodes, right? So we will pass one node that we have got here. This node we have to pass onto the map, right? And we will have our on the list, and we will get all the its neighbors, right, at a time. Okay. So if see a node have neighbor, right? So he have all neighbor, right? So if we'll talk about A to B and B to A, so we will get first A to B. We have neighbor A to B, means B is the neighbor. Next second time we will come B, so it will get A again, right? Neighbor as a neighbor. So that's why we are taking like this. Okay. So check if we have already seen in this node, right? So A has already came as a node, right? So A is coming again, right here. So what will happen? We have to check if if we have the one set, right, seen, and if seen contains, previously we have taken, right, if seen contains this neighbor, what, this neighbor, you are neighbor, right? If seen contains this neighbor, then what we have to do? We have to return what? False. Means this is already visited. We don't need to visit again. Now, if we'll talk about if that is not the case, right? Means we are not visited that node, then we have to put the neighbor onto the stack, correct? And we have to record that it has been seen. So that we have to do, our stack is here, right? First we will push, right, that previously we used to do. We will push our neighbor, right? And this neighbor has been on the now a stack. So we have to also add on to set scene. Now we are doing that. We will take the neighbor. Now neighbor is also here on the stack and scene. Now what we have to do? We have to remove the link that goes back as a opposite direction, right? How we will, the main thing that we have to discussing, how we will remove the opposite direction link, as you can see. Okay, this is the opposite direction edge, right? How we will do that? We have our adjacency list. From the adjacency list, this is our adjacency list. Dot will do get, and we have to pass the neighbor. Means if we'll talk about, this is the node first we have, right, this node, and what is the neighbor? This is B, right? So when we come to here, right, B, A is already visited. Now we are going to B. So B has what? Neighbor A again. So when we are coming to here, we have to remove this one, right? So for B, A is a neighbor, correct? So we will get our neighbor, and its neighbor is A. So we have to remove our what? Node. How will do that? From the list we will do remove, and we have to remove that node from the list, and that is done. So I was talking about this part, how we will remove our opposite direction link, right? Opposite direction edge of the neighbor, right? So this is our first approach, in which this is our first strategy or approach, you can say, in which we will remove the opposite direction of the edge from the adjacency list from A to B, and not we will take B to A. And for that, what we have to take? We have to take if stack is empty, then we will go to into the loop, while loop, this loop, right, this loop, and then first we will get from the stack dot pop, and then we have our node. From the then we will make a for loop, right, this for loop, and this for loop will get we have to pass that node one by one. We will have all the neighbor will get, right? And first first condition, what we will check? We will check that if that is already in the scene on the set, right, it means we don't have to
go beyond, right? We don't have to go beyond, right? We to continue, and we have to return false here only. Now if they are not if they are not on the scene or a stack, right? Means that we have to on the stack, right? Scene, then we have to do set, sorry, then we have to continue, and then first we will, to maintain the record, we will put onto the stack and on the scene. Now in finally what we will do, we will remove the neighbor node, opposite direction neighbor node. How? Adjacency list dot get neighbor, and then we will do remove what? Our node, that node is in the opposite direction, that is opposite edge, you can say. Now if we'll talk about the strategy 2, right? A strategy strategy 2, right? The first strategy, we have removed the opposite direction, right? So now if we talk about the second strategy, is instead of using scene, right, scene set, right, to use a scene map, we were using scene, right, as a what? Set. But we are not taking as a set, we will not take set, we will do as a map, right? We will map as a scene. Okay, so to use a scene as a map, right, that also keep track of our parent node, right? So we got a node from, we will pass a node and we will get our parent node, right? So every node has its parent, right? Parent node, correct? Every node has its parent node, right? So we call this map as a parent, and we'll say that this is our parent map. Okay, so then when we iterate through the neighbors of a node, we ignore the parent node as otherwise, right? So it will be detected as a trivial cycle, and when you can say, we know that the parent node has already been visited by the point anyway. When if a node we are going to traverse, right, if he has been traversed already, then we will go to the child, right? Either which child we are going. Okay, so if we are here, means we have already visited this one, right? So we do not need to go here again. So it is saying we have to, if we if the parent node is already visited, then we do not need to go to again. Now the starting point, if we'll take 0, right? 0 is the implementation has no parent. If we'll pass 0, means no parent, there is no parent, right? And if we'll pass and then we can put it as what? -1. Okay, if any node, that is, let's suppose 0, has no parent, means we have to return as what? -1 we will take, or we will put it as -1. So at first it is little more difficult to understand why this strategy even work, right? So a good way to think about it is to remember that, like the first approach, right, we just want to avoid going along as we have already been seen, right, in the opposite direction. I will talk about the opposite direction. So the parent links prevent that, as each node only enter the exploration once. So imagine we are walking through a maze, we with the condition that you are not allowed to go back any path you have already seen. So if you still somehow end up somewhere you were previously must have been in cycle, right? So as I told you, if you have already visited this one, so you cannot go back, right? This is the condition. Okay, and that's why we will follow this one, we will prevent going to the parent node. So this is our strategy 2. Next, previously what was doing, we cannot, we were removing our opposite direction, we are following this direction, but we are not going this direction. Now what will happen, we will not go back to our parent one, that's all. And so that what we should do, so as I told you, first of all, the map, we will maintain the map, right? So if this is our integer, right, and this is also integer, okay. So now what we have our parent, and parent is what? We'll take new has map. That is done. Okay, now what we have, this is our parent, right? Now we have to use this map to keep track of how we got into each node, right? This parent node we will use as what? To keep track of how we got into each node, right? So what we have to do, we have to say parent dot, we will use put, and then we will pass 0 minus 1. Means this is our parent that I was talking about. Means the parent node has what? 0 node, but it doesn't have any parent, right? No parent means minus 1, correct? Now if we'll talk about the loop, right, while there are nodes remaining on the stack, right, what we have to do, we know that we will make while loop to all the stack element, right? Stack dot is empty. This is our loop, right? We will move until it is not empty, right? So first, what is the way? First we will stack dot, we will do pop, and then we will get our element, and that is what? Our nothing but our node, right? So this is our node. Now this node is done, right? Now we will check on to the adjacency list, right? So do we have our adjacency list dot get, and we will pass what? This node, right? And this is what? We'll get one by one its neighbor. I'll take it int neighbor, and this is what? Our for. So this for, we have to pass on the adjacency the node, and we will get its neighbor. So don't look at the trivial cycle, and for that what we have to do, we have to make a condition. We don't want to see the trivial cycle, right? And that is what we have, parent dot get what? Node equal to what? This neighbor that we have taken neighbor, right? We'll take this one. If that is equal to this one, parent node, right, what we will do, we will continue. We are not going to do anything, continue work, right? Now again we will check if this is already in the parent, right? So we'll see parent dot contains key, and we will pass our neighbor, right? So it means we are checking if we have already seen this node, right? If this node is already in the parent map, right, what we'll do, we'll return false. We are not going, because we have to restrict to go back to the parent node, right? So if and that maintain our what, that will be our must be a cycle, right? And so that we have to return false. And so otherwise we will put the neighbor onto the stack, and we have to maintain the record that it has been seen, right? So what we have to do, we have to do stack first, then we know we will do push, and we will pass the neighbor here. Neighbor is also on the stack. Now we will add on to the parent dot, will do put, and we will pass what? And our neighbor and its parent as a node, right? So this is all I have, right? Now the best strategy for this problem probably is the second one, right? We are using map, right? And because it doesn't require modifying the adjacency list, we are not going to do another operation for the adjacency. We are just maintaining our parent map, and for that we can say that this is better for the solution. This is best approach we have. And for more complex problem, we can use the first strategy, right? That can be used for the program, right? So in the next part, what we can do, we can write all the code. So let's go to the our code section and we'll do hands-on. Okay, I'll recommend you what you can do. You can pause this video here and try by your own. Okay, so if you are getting hands dirty, let's continue to do coding into the uh, coding browser. Okay, let's continue. What n is given, number of nodes we have given, all the edges we have given, right? So first of all, if we'll talk about the first strategy, right, what we are doing there, we are taking the adjacency list, right? What is the adjacency list? We have taken a list, right? And this list is what? List of list. Okay, and this okay, this list of list, and internally it was taking what? The list as an integer, right? This integer. Now what we will do, we will take adjacency list, adjacency list, right? This is our adjacency list, and then we'll take as what? New array list, array list. That's all. Now our adjacency list is we have written. Now we'll make a loop, right? And that loop will take from all the nodes I equal to 0, right? And then it will go to I should be less than n, right? Let me put little space, right? And then I plus plus. So we are moving all the our nodes, right? So this is all we have, right? What we have done, first we have maintained our adjacency loop, right? List, and then we have came to our all the nodes, right? We are traversing all the nodes. Okay, now what we have to do, we have to take this adjacency list, right? And this adjacency list we have to uh, add, right? Now we have to do add, and then we have to pass what? uh, Internally we have to initialize all our neighbors, uh, adjacency neighbors, right? How we'll do that? Adjacency yeah, neighbor you can say. Then this is what we have internally, we have to initialize like this we have to do here. Okay, so this part is also done. Now all the initialization is done here. Now what we have to do, we have to go all the edges, right? What edges we have given, this is our edge was given, right? And for that what we have to do, we have to make a for loop, and we'll say that one by one array from 2D we will get a single array, right? And that is what all neighbor we have of a edge, right? From what we are getting, from edge we are getting, right? Edges, from edges we will get one edge at a time. Okay, now this adjacency list we will create, right? We have to put the some value here. Now first we will get the edge at what the given is, what we have at index 0. These things we have already discussed already, right? You can go back and you can see how we have construct this one, right? Now if we are here, right, now we have the age at 0. Okay, so some value will be there, right? Now we have to add what? Add age 1. What is at age, what is as is 1. Okay, that is 1. This is array, so we have to 0 and 1 we have to take, right? Like this. So why I'm taking like this, because you have given a set of what array, right? And each array contains it like 0, 1, right? These are our given 0, 2, like these are our neighbors, right? So we have got this one, right? We have got this as a edge, and at index 0 what we have its neighbor what? 1. So we have to take this one. So first we have taken edge at 0 means this 0, and edge at 1 means this 1. If we'll talk about this one, so this will go to edge 0 and 2 will go to edge 1, right? like this we have maintained. So second time what will happen, when we come to here, right, we are maintaining our adjacency list, right? So what will happen, uh, we have to maintain all the edges, right? So first we come for the node 0, we have the neighbor 1. For now we have to, for node 1 we have to take what is at 0. So reverse back we have to do. Okay, this is done. Now if we'll talk about the parent one, right, this is done, right? Now if we will create a parent, right, map, and that parent map will do what, uh, we'll talk about, we are talking about the strategy 2. If you want to do strategy 1, you will not take this map, you will take the set. I'm taking parent 1, the strategy 2, right? So we'll take integer map, right, and this is our what, parent, correct? And this is what, equal to new has map, like this, correct? This is done. Now we will put the parent that we have already know, parent, and dot what, will put some value, and this is if we are taking 0 as a parent, so it doesn't have any parent, super parent, we don't have any super parent, so we'll take no parent, means we have -1, correct? That we have already seen. Some space is coming. Okay, it's fine. Now we have the stack, right? Now we have what stack we have. So what we will do, we'll take a stack, and that stack will contain what, integer, right? So we'll take integer, and this is called stack, correct? Now what we have to do, we have to initialize this one, new stack, like this we have initialized. Now for first node 0, right, we have to put on stack dot will push, so we have done 0 here. Now parent is here. Now we have to make a condition in which we will check, check one by one, right? If stack is not empty, not equal to what, stack is empty, correct? If that is not empty, then we will move to, we'll go to this loop, right? And we will first take one node equal to what, from stack dot pop, right? We will get all the its node from the stack one by one. Now what we have to do, we have to go to our all the neighbors of the that node. So each node will get what, how, nei, I will get from what, we have to pass the from the adjacency, right? Adjacency list and sorry, list, and then what we will do, we'll do get, and we have to pass the node. I think this step you have done, you have understood. We have already seen this one multiple times. Now what we have to do, we have to check the condition, and condition is what, first we will check the parent, right? If parent contains that node, right, so we'll take if condition, and we'll see parent map contains what, this node, right? Get, and we will pass to node, right? If parent node have is equal, is as a neighbor, you can say neighbor is neighbor, then what we have to do, we have to continue here, we will not do anything. In another condition, what we will do, as we had talked about, if parent contains, right, what parent contains key as what, nei, neighbor, then what we will do, we will return as false, return false, right? Now what we will do, false, yeah. Now what we will do here, so parent, if parent contains key, means we have already visited, we will not go, we can't go back. This condition also done. Now if this is coming the first time, so we have to maintain our stack, so that we have to take a stack dot push, and we will pass our neighbor, and so that we will update our parent too, because we have to maintain our map, and that's why we will pass neighbor and its parent node, that is node, right? That's all done. And finally what we will do, we will return parent size equal to what, that we the condition we are talking. Once we have done our while loop, we will check, we will return what we will return, we will return parent if parent dot size, right? If parent dot size like this is equal to what, given n, right? it means it means it will return true or false. Okay, this is cycle or not. Let me compile this code. Okay, sorry, here we have not did here. Okay, I think now it should work. Yeah, it should work. Yeah, it's working fine. So thank you guys. You can continue the first approach, and please comment, subscribe channel, and please promote this channel as much as you can. Thank you so much for uh, all your effort to having, liking, sharing, and doing comment. Thank you so much.